Okay, so here is a real world situation. We have a farmer that has 2,400 feet of fencing. And this is a real world situation, right? We've got a person who has this much of a given item. And now, what does that person want to do with that item? This farmer, with his fencing or her fencing, wants to enclose a rectangular area that borders a straight river. So here's sort of the idea. We've got this river flowing here, and we want to enclose a rectangular area around the river. Okay, cool. So now we've got a sort of a picture of what's going on. And then they want to divide it into 3 pens with fencing perpendicular to the river. So if we want to divide this into 3 pens, well then we have to run the fencing perpendicular to the river as such. So now we've got our 3 pens, we've got our rectangular area, we've got the situation that the farmer is after. And now here's what you could imagine. If you build this fence super deep into the property, the pens would be very narrow and might not have a lot of area. If you build this pen very wide, not very deep into the property, along the river, the amount of area in your pens would also be very small because it would be very sort of thin. So the question is, what are the dimensions of the rectangle that yields the largest possible area? And if you really reflect upon this would be a real problem, because if you've got chickens or whatever other type of animal you're storing in these pens, you're probably going to want to give them as much area as possible to roam. But you can only afford so much fencing. So if you purchase this much fencing, how can you maximize your dollar by giving yourself the most area for your barnyard animals to run around? Well, that's the question. Okay, what are we trying to do again? We're trying to yield the largest possible area. So our challenge is going to be this. We need to find an area function. Once we find an area function, we need to find where the area function hits a maximum. We're looking for a largest. So we are trying to be very clear, like here's our area function, and the goal from there forward is to maximize area. Okay, now how are we going to compute an area function? Well, certainly you can see that the area would be a rectangle. So the area would be nothing more than length times width. Whatever the 2 dimensions are of the rectangle, you multiply them, that's going to give you the total area of the rectangle. And now the question is, what are the dimensions of the rectangle? Well, we know that among all of the pieces of fencing, we have 2,400 feet of fencing. But then the question is, how deep into the property do we go? Do we go very deep? Do we go not very deep? Well, that amount of depth into the property could vary. Let's use a variable to describe that. So let's describe x to be the depth of the fence. We don't know how deep we're going to build this. If we knew how deep we're going to build this, the problem would be solved. But now here's the thing to think about. Once we know how much depth is along each of these pieces, I claim we then subsequently know what the length is. Because you see each of these pieces, there's 4 of them, that's going to be 4x amount of fence in terms of length. That's 4x feet of fence. Well, if we have 200 or 2,400 feet of fence, well then if there's a total of 4x pieces of feet of fence going up and down, then the rest is going to have to go side to side. So if we have a total of 2,400 feet of fence, if we subtract our 4x, namely the length of the fence that's going up and down, that's going to give us the rest of the length, which is the length that goes sideways. But now, with this in place, we now can compute what the area would be. The area is going to be 2,400 minus 4x times x. That's the area of the plot of land. Which, if you run the numbers on this is what? 2,400x minus 4x squared. Now we've got an area function. What do we do with it at this point? Well, once we've got our area function, we need to maximize the area. How are we going to find a maximum point? Just like we always do when we're given a function. Given a function, take the derivative, a prime, that's going to be 2400 minus 8x. Set that equal to 0. Bring the 8 to the other side, divide away by it. You'll get x equals 300. So we have one critical point at x equals 300, and the question remains, is that critical point a maximum or a minimum? Well, we're going to have to test on both sides to find out. We can test a value over here, 0's over there. Test a value over here, how about 400? Something like that, something that's just easy to compute with. Well, and what do we test into? Because to see if this is a maximum, we want to know whether our function's going uphill or downhill. We need to test first derivative, which we actually already have. So we need to find a prime of 0. Plug in 0, that's going to be 2400. That's positive. So it's conceivable that at x equals 300 we hit a maximum, but that's not known yet. We have to see whether or not the function goes downhill on the other side. What about a prime of 400? That's going to be 2400 minus 3200. Ah, that's negative. Downhill, slope. Downhill, first derivative describes slope. And yes, we can see indeed that x equals 300 is not just any point, but it is a local maximum point. And that means, if you think about this in context, if you built your fence out from the river any more than 300 feet, you would be losing area because the function that is being described here by this picture going up and down is our area function. So any more than 300 feet, you'd be losing area. Any less than 300 feet, in terms of the depth that you would build away from the river, you would also be losing area. In order to get the maximum possible area in this situation, 300 feet is how far you have to go. So x equals 300 is our parameter that we will work with, and what is our solution? Our solution was not just to find how deep into the land you have to go, but to find the dimensions of the rectangle. So here, the dimensions are going to be what? 300 feet is going to be one of them, and the other dimension is 2400 minus 4 times that. Well, 4 times that is 1200, 2400 minus 1200, 1200 feet. Any other rectangle different from that in measure is going to have less area. This is the measure of the maximum area, or the dimensions of the rectangle with the maximum area. And the long story short on how to get to a solution like this, and really where the problem lies, is can you take the information from the problem, can you encode it mathematically into a function to describe the characteristic of interest? Because if the answer is yes, and you can produce that function, then it's a matter of taking derivative, setting equal to 0, testing on both sides, and you'll have it. And well, let's go through another example to get ourselves more familiar with this.